Theorem 5.6 is referred to as the additive interval property. Suppose that f is integrable on the three closed intervals determined by a, b, and c. Then the definite integral from a to b of f of x dx is equal to the definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx. This is one of these properties that makes a lot of sense, especially if you think about it when the context of area makes sense. Suppose that f is non-negative. It doesn't have to be that for this condition to hold. But if you think about like the total area from A to B, if it made sense, then pick any point C that's in between A and B. The area under the curve from A to C plus the area under the curve from C to B would give you this total area of the under the curve from A to B, and that's one of the ways you can kind of think of this additive interval property. In example 5, they ask us to use the additive interval property to find the integral, definite integral from -1 to 1 of the absolute value of x. Let's go ahead and do that. So first thing we can do is we can kind of go ahead and split it apart, because we know that the absolute value of x, it changes its expression at 0. This is equal to x when x is greater than or equal to 0, but it's negative x when x is less than 0. And for that piecewise defined function, that 0 is in between -1 to 1. So we can write it like this: the integral from -1 to 1 of the absolute value of x dx is going to be equal to the definite integral from -1 to 0, absolute value of x dx, plus the integral from 0 to 1 of the absolute value of x dx. On the interval -1 to 0, absolute value of x is equal to -x, plus on the interval from 0 to 1, the absolute value of x has the expression x dx. So we're able to split it apart like this. And if we look at each of these two definite integrals, we can look at them in terms of the area. It's going to lie above the x-axis. So it's each of those pieces is non-negative. Here's the graph of -x. Here's the graph of x. So we can figure out the definite integral by calculating the area of a triangle in this case. We know that the area of a triangle is 1/2 base times height. So the area of this thing here is going to be 1/2. It's going to have a base of 1. It's also going to have a height of 1. So the first triangle has area 1. Likewise, the second triangle, this is going to be 1. This is going to be a height of 1. Also has an area of 1/2. So the final answer is going to be 1/2 plus 1/2, which would be equal to 1. Let's take a look at Theorem 5.7, properties of definite integrals. Suppose that f and g are integrable on a closed interval a to b, and k is any constant. Then k times f, the sum or difference of f and g, are all going to be integrable on a to b, and we have the following properties that hold. So the first property is essentially a constant multiple rule that says if you have a constant times an integrand and a definite integral, then we can move that constant to the outside as a constant multiple. Property 2 says that the definite integral is a linear operator. If you have the definite integral of the sum or difference of two functions that are integrable, then the answer to that is simply the sum or difference of the definite integrals of each of the two functions individually. These are two properties that we'll be using a lot. A lot of times we don't necessarily explicitly write all of this out every time, but in the back of our heads, as we're moving through a lot of the calculations in the next couple sections, we will be using these results regularly. For example, in problem number 6, we're asked to evaluate the definite integral from 1 to 3 of negative x squared plus 4x minus 3 dx given the following information. We are told that the definite integral from 1 to 3 of x squared is 26 thirds. The definite integral from 1 to 3 of x dx is 4. And the definite integral from 1 to 3 of dx is equal to 2. What we can do is use our properties from the last slide to simplify this. I can rewrite this definite integral as the definite integral from 1 to 3 of negative x squared dx plus the definite integral from 1 to 3 of 4x dx, and then minus the definite integral from 1 to 3 dx because the integral is linear. I can now use the constant multiple rule, which would be number 1, to factor out the constants from outside of those integrals. And now with those factored out, we can use the given information to find each of these basic pieces. For example, we know that the integral from 1 to 3 of x squared dx, that has a value of 26 thirds. Plus 4 times the definite integral from 1 to 3 of x dx has a value 4. Minus 3 times the definite integral from 1 to 3 dx has the value 2. So we can go ahead and plug in those results. We're going to get negative 26 thirds plus 16 minus 6. This is equal to negative 26 thirds plus 10, which is negative 26 thirds plus 30 thirds, which should give us a final answer of positive 4 thirds. So the final answer is this definite integral has a value of positive 4 thirds, and essentially the way we found that was by breaking it up, doing the definite integral of each piece, using constant multiple rules, and the values for each individual piece. So where these different things are coming from, we're going to discover a shortcut formula to that in the next section. Before we move on, there's one more thing that we want to highlight, and this is preservation of inequality. If f and g are continuous on the closed interval a to b, and suppose that 0 is less than or equal to f of x, which is less than or equal to g of x, for all x between a and b, then the following properties are true. If f is integrable and non-negative on the closed interval a to b, then the definite integral will also be non-negative of f on the interval a to b. So that means that 0 will be less than or equal to the integral from a to b of f of x dx. Also, if f and g are integrable on the closed interval a to b, with the property that f of x is less than or equal to g of x for all x in the closed interval a to b, then the definite integral of f from a to b will be less than or equal to the definite integral of g over a to b.